Good morning, everybody. Today, let's see the properties of Fourier series. In the syllabus, they have just said that it's properties of Fourier series and the problems. So we have to be seeing the proofs of the properties along with the properties. Understand? So we shall go through the different properties along with their proofs in this session. So first property is linearity property. Now, in linearity, if we have to say a transform is linear, so we need to have two signals first. Okay, that's why we have taken x of t and y of t. And Fourier series, if you see the Fourier series coefficients of this, that will be x of k and y of k. Understand? But if we have to say that Fourier series is linear in nature, so then it's not only the signals, but it's the weighted signals, and there's some what we need to consider as we have seen here. Understand that? So if you apply the transform on this, so this is how it is going to look like in frequency domain. Yes, we need to go with the assumption that both x of t and y of t would have the same fundamental period t equal to 2 pi omega naught. So one should understand that we are applying Fourier series only to the signals which are periodic as well as continuous in time. And we know that all continuous time periodic signals are periodic with fundamental period t equal to 2 pi by omega naught seconds. Understand? So let's see how we can prove this. Everyone understand? We have to start from the equation for the coefficients. Coefficients, so x of k is the coefficients of x of t in frequency domain, that is given by this. So this is called as the analysis equation. We are analyzing the frequency information in frequency domain. Okay. Similarly, this is the coefficients of y of t in frequency domain. So these two are the frequency domain signals, or we should say spectrum. These two are spectrum of x of t and y of t respectively. Okay. Now, after having x of k and y of k, let's write the equation for z of k also, because z of t is the weighted sum of the signals. Understand? So let's take z of k, which again is written in the same fashion. Fine. And we know what is z of t from the given signal here. Z of t is sum of the weighted signals. So let's substitute z of t as sum of the weighted signals. That is this. Understand? After you take this as sum of the weighted signals, now take this integration along with this 1 by t and this exponential to both these signals. So arrange in this way. Okay. And if you leave this a, what is 1 by t times integration of x of t power minus j k omega naught t? So that needs to be understood. So what is that? That would be this. This is x of k. If you take a aside, okay, so what is left is x of k, and if you take this b, and what remains there is y of k. Fine. So what it tells you is, if you have a scalar that is a and b, if you have a scalar that's a and b, here a and b are scalars along with the signals x of t and y of t. If it is so, what you can do with Fourier series is, you can always keep aside this the scalar and operate only on the signals. So that is what is true, because the Fourier series is linear in nature. Understand that? So let's go on with the next property. That's time shift property. It says it's a time shift. We are shifting it in time. Fine. We could even shift it in frequency. That will be called as frequency shift, which we'll be seeing in the next property. Okay. But now we should understand that we are talking about time shift. So time shift means this is the time domain signal. X of t is the time domain signal. X of k is the frequency domain signal. Understand? So we have to shift it in time, means x of t needs to be shifted. And how it is being shifted? It is being shifted to the right by t naught units. So it's a right shifted signal. So whatever shift you have here, so that needs to come as a power to this exponential along with the signal x of k in frequency domain. So since it is shifted by minus t naught, in the power you need to have minus t naught. That's why it looks like e power minus jk omega naught t naught into x of k. Understand this point? Now you can just compare this with the Z transform time shift. In Z transform, what we used to do, what is the Z transform of x of n minus n naught? The Z transform of x of n minus n naught is z to the power minus n naught into x of z. So you can consider this as z in this case. In the frequency domain, this is z. Jk e power jk omega naught. If you consider this as z, it is z to the power minus t naught types. Understand that? Why it is minus t naught? Because there is a shift which is minus t naught. So that's why minus t naught should come as the power. Understand that? So let's see how this can be proved. So here we have x of k, which can be given by this, and we have y of k, which can be given. Why we are dealing with x of k and y of k? See here, the signal x of t has the transform x of k, and signal y of t has the transform y of k. And what is y of t? What is y? Why we are writing y of k? Because I need to deal with y of t. What is y of t? Y of t is the time shifted signal. Okay, so bring this time shifted signal in place of y of t. Okay, and see what happens now. So we are substituting m as t minus t, or t minus t naught is being substituted as m. Why is that? Why is that? See, in all standard transforms, we have one unit of time, or we have just one unit. We don't have t minus t naught sorts. Okay, so let's see this as x of m instead of looking at it as t minus t naught. Let's see it as x of m. Now, if t minus t naught is m, what is t? So that needs to be understood. If t minus t naught is m, what is t? Then it is m plus t naught. This t would become m plus t naught. So that is what we should be doing. See here, t minus t naught is substituted as m. Okay, since this is m, this t naught, the t we had here needs to be substituted as m plus t naught, because t is m plus t naught, this t being taken to the right hand side. Now we are dealing with two exponentials here. Since you have m, okay, the exponential which comes in terms of m, you associate that exponential with this x of m. Okay, and the exponential which is not a function of m can be taken outside, because here when we say this t says it is for one period. And what is that one period? Now that one period is the function of m. So m is running for one period. That is what is the integral duration. So whatever is the function of m, keep that inside this integral, and the exponential which is not the function of time, you bring that outside. See here? Now if you split this, you have two exponentials. One is e power minus jk omega naught m. Keep that with this, and another exponential e power minus jk omega naught t naught. Bring that out. Now, how does this look like? How does this look like? Now, earlier we were dealing with as t, right? So if you just consider this as t now, okay, it will be x of t, this exponential again in terms of t dt would have been the case. So what is this equal to? This actually is equal to x of k. What is the difference? Instead of dealing with t, we are dealing with m. Just the notation is the difference. Okay, so instead of looking at t there, we are looking at m. So there is no difference other than that. So this term can be looked at as x of k. Okay, that is what is written here. So this is how it is proved. So which property is this? This is time shift property. Fine. In time shift property, what we are doing, we are associating an exponential to frequency domain signal. Okay, with the shift whatever we have in time domain. Understand that? So this is regarding the time shift property. Let's go on with another property, that is frequency shift. I was telling you about. Okay, in the previous case we have seen time shift. In this case we are seeing frequency shift. In time shift, this x of this is time domain, this is frequency domain signal. So x of t was shifted in time domain, whereas x of k will has to be shifted in frequency domain. So this is frequency shift. So k is the frequency here. So that needs to be shifted. See here, k is being shifted. So if you shift k by k naught, see here, the exponential in time domain is e power j omega naught t. The exponential in frequency domain was what? The exponential in frequency domain was e power j k omega naught here. But here it is e power j omega naught t. So here you will have t, here you will have k in the exponential. But since there is a shift here by minus k naught, this has to be having the power plus k naught. So frequency shift will have frequency shift minus k naught will have plus k naught power here along with the exponential. Whereas in the time shift, what was happening? See, in time shift, if it is minus t naught, same minus t naught used to come as the power to the exponential in frequency domain. But what's happening here in frequency shift? If the frequency shift is minus k naught, it would come as plus k naught power in time domain. This is the important thing that you need to understand. And what is the other difference? The exponential here we have considered is a power j omega naught t, because this is not a function of k. The time domain is not a function of k. So the exponential, the basic exponential that we consider is e power j omega naught t to the power k naught. What was happening in the previous case? It was e power j k omega naught here. It was e power j k omega naught to the power minus t. Okay, so you have to understand that. Fine. So let's see how to prove this. Okay, if you have a shift in time, you will have an exponential associated with x of k. If you have a shift in frequency, you will have an exponential associated with x of t. Understand? So this is something that one needs to see. Now let's see how the proof goes. Now consider this equation x of k, which is obtained by applying Fourier series. This is the Fourier series coefficients of x of t. Similarly, we have seen y of t for which is the coefficient of y of t. Fine. Now in place of y, you bring this x of t into you. You have this, right? Okay. So y of t, whatever is there in as y of t, that needs to be brought in place of y of t. Though there is a shift, okay, though there is a shift x of k minus k naught, okay, that shift will result in this exponential in time domain. So that exponential in time domain along with this signal is substituted in place of y. Okay, again as you see, we have k minus k naught. Now this, how does this equation look like? This is very similar to this. You see this? This is very similar to this, except that this k is k minus k naught. Except this k is substituted as k minus k naught. So if this is k, this is x of k. Understand? If this is k minus k naught, what is this supposed to be? So this is supposed to be x of k minus k naught. That's very simple proof. Just have to bring this time domain signal in place of y of t. Understand that? So if you bring it in terms of in this case, okay, so just see the power. Since the power is in terms of k, it is x of k. Since the power is in terms of k minus k naught, it is x of k minus k. Understand that? So this is called as frequency shift. Fine. Yeah. Now let's go on with the next property, that is scaling. Now it just says scaling, but we need to be careful regarding where what is being scaled. Is the amplitude being scaled or the time is being scaled? So seeing this, can you tell me what is being scaled? So the time is being scaled by a factor A. A is a scalar there, okay, which we are using to scale the time. So that's what is called as time scaling property. So if we scale the time by a scalar A, okay, what should we be having on the right hand side? So earlier, before scaling, it was x of k, okay. You can see after scaling also it is x of k. What does that mean? What does that mean? It means that scaling the signal, scaling time scaling the signal has no effect on frequency domain signal. Okay, so time scaling would not change the coefficients, is what one needs to understand. Let's prove that this was not happening. This was not happening in Z domain. It used to change in Z domain. Okay, but here the frequency domain signal will not change if you scale your time in time domain. Understand? So how is it going to be? If x of t has the fundamental period t, this x of t has the fundamental period t, then z of t, that is x of at, has the fundamental period t by a. Understand? So it is about fundamental periods. Your fundamental period would change. Fundamental period of x of t and x of at are different. If x of at has the fundamental period t, then x of at will have the fundamental period t by a. Understand that point? Now, with that knowledge, let's move on. So consider again the coefficients of x of t. Okay. So since we know this equation, I can even write the equation for z of k. Okay, but with what difference? With what difference? It is very clearly being told. If it is x of t, if x of t is having the fundamental period t, then x of at will have the fundamental period t by a. Since we are dealing with x of at here, so z of t is x of at. Since we are dealing with x of at, the fundamental period needs to be considered as t by a here, and t by, in place of t just have t by the capital T, you have capital T by a, because we have time scaled the signal. Understand? So how can this be arranged now? This can be arranged as, so it was 1 by t by a, so it is done as a by t here. So in place of z of t, we have x of at. Now again, I don't want to see two things here. Just substitute at as m. Understand that? Okay, and if you if you say it is dt, okay, then it would be 1 by 8 times dm. If you substitute at as m, okay, then dt can be represented as 1 by 8 times dm. Understand that? So if you bring in this in place of dt, and if you bring this 8m in place of at, the equation looks like this. Okay, now this 1 by a can be brought out because this the scalar has got nothing to do within the integration. So bring this out. If you bring this out, it was a by t into 1 by a. So a and a goes off and you'll be left with 1 by t. We'll be left with 1 by t. Okay, and what is this? What is this now? So it's again x of k. Instead of seeing it as t, we are seeing it as m. That's it. So it is 1 by t into x of. So it's 1 by t is here. So L 1 by t into this is anyways going to give you x of k. So we started with x of k in frequency domain, and after shifting it in time domain, you will see that we again end up with x of k. So what is the uh, thing that we need to understand here? The point that we need to understand here is shifting in time domain has no effect in frequency domain coefficients. Understand? So this is the time scale property of Fourier series. Fine. So just how to remember this? If you understand the thing, if you understand the point, then it would be able to will be able to understand the remember the property. So understanding would help remember. Okay, so just don't mug up the things blindly. Fine. Let's understand what it says and then try get that result. Okay, so let's see the next property, that is time differentiation. What happens if we differentiate in time? X of t is x of k. The Fourier series of x of t is x of k. The Fourier series components, I should say, not Fourier series of. Fourier series is representation of x of t. Okay, so the components of x of t in frequency domain are x of k's. So what happens if you differentiate it in time domain? What is this saying? If you differentiate it in time domain, then a factor jk omega naught comes along with x of k. What was happening there in z domain? You can compare and you can see what was happening there. If we associate n with x of n, if we associate n with x of n, then it used to be minus z times d by dz of x of z. Okay, so it is differentiation in z domain there. So it is differentiation in time domain. So there is a difference. Okay, so we are not differentiating it in frequency domain, rather we are differentiating in time. If you differentiate it in time domain, then you need to have an additional component j k omega naught along with x of k. So how is this true is what we'll see. So this is the basic equation. We're starting with x of t, mind you. Okay, because I need to differentiate x of t with respect to t, right? So let's start with x of t. Till now we were considering the analysis equation, we're not considering the time domain equations. See here, whichever the proof you see, we used to start with x of k, not x of t. Understand that? But here we are starting with x of t. Why? Because we need to differentiate x of t with respect to t. That's why I have this synthesis equation. So x of t is called as synthesis equation because we will be able to build x of t provided we are having x of k as the coefficients. Understand? So if you differentiate this, what happens? This is what is going to happen if you differentiate this with respect to t. Okay, it's d x of t by dt with respect to time you are doing. So this in this summation and x of k there is no t at all, so you can consider this as the constant. Okay, and you can differentiate just this because this in this exponential we have got t, so only this exponential would be differentiated with respect to t. Okay, keeping this summation and x of k out of differentiation. Okay, see, so summation and x of k have come out of differential operator, and only the exponential is being differentiated. So how does it look like now? Here it's e power j k omega naught t into j k omega naught, because it's a function of t. We are differentiating with respect to the t. That's why this becomes. You all should be knowing this. Fine. How to differentiate now? What's happening now? This j k omega naught is brought along with this x of k. Just rearrange this. Now compare this equation. Compare this equation with the equation for x of t. Okay, now seeing this, can you tell me what is going to happen? This is a little tricky. Okay, because if you cannot compare this properly, you should know what is the result that we are behind. Fine, so let's understand this. See, we have to read it like this. If x of t has the coefficients x of k, then this is the equation we come across. If x of t has the coefficients x of k in frequency domain, this is what the equation we come across. Understand? So similarly, how you can read this equation? How we can read this equation? Here, x of k is the coefficient of x of t. Therefore, can we say jk omega naught x of k are the coefficients of this differential of x of t? Yes or no? Yes, we can say that. Just compare these two equations. Okay, x of k's are the coefficients of x of t. Okay, if we can say that, we can also say jk omega naught x of k are the coefficients of differentiation of x of t with respect to t. So that's why we can say this. Since x of t has coefficients x of k, okay, hence dx of t by dt will have coefficients jk omega naught x of k in frequency domain. Understand? This is what is called as differentiation in time domain property, which is there with the Fourier series. In Z domain, we had differentiation in Z domain property. In Fourier series, we have differentiation in time domain property. Okay, so this is how we prove this. Let's go on with another property, that's convolution property. We had convolution property in Z domain also, Z transforms also. Okay, the same property is being seen for series. So if you have to convolute two time domain signals, we can multiply them in Z domain there. Okay, similarly here, if you have time domain signals, okay, which are being convolved, we can what we can do, this convolution operator in frequency domain would become the multiplication. Okay, but one difference is what, it was just x1 of z, x2 of z there, but what's happening, there is an additional t, which is actually the fundamental period of x of t and y of t. You should understand, when we are dealing with two such signals, okay, so the assumption that one needs to make is both these signals should have the same fundamental period, because since we are dealing with the Fourier series, what we are looking at here are the continuous time periodic signals. Understand that? So because of that continuous time periodic signals, we have to talk about the fundamental period. So this fundamental period t is actually fundamental periods of x of t and y of t. Okay, so that t would come along with the product term in frequency domain. So how is that? Is what we are going to look at now. We have x of k, which is being written as this. Okay, so if x of k is that, y of k is this. Now in place, so for these two, x of k we have written y of k. Let's see what is z of k. Now, what is z of t? Z of t is actually the convolution of x of t and y of t. So let's substitute that in place of z of t. See here, in place of z, we are convolving x and y. Fine. Now, what we should know is, this is what is the convolution looks like. So this is something that we should have dealt with in module 2. Since we didn't cover module 2, it has got a lot of sketches, finding out convolution sum, finding out convolution integral, all of that is there. So we will be taking that up when we meet in the college. But as of now, you understand, this convolution operator on x of t and y of t would give you the convolution formula as this. Okay, just substitute this formula in this place. Fine, it looks like that. So that means in place of x of t convolution y of t, we have brought this. Fine. Now just change the order of integration. So what you can do is, x of l is there, right? So x of l dl is there. You can take these two together, and t is there. You have to rearrange this. You have to rearrange where you will have dl, where you will have dt. Fine. So that is what we are looking at. So where t is there, associate uh, the exponential with that and dt with that. And where t is not there, bring that along with this. So just separate this from the rest. See, we have separated this function of L from the rest, and wherever T is there, we have grouped that together. Fine. Now, substituting T minus L as M, T minus L as M, what we can do is this. Where is T minus L? See, T minus L is here. This is M. Understand? If T minus L is M, okay, what is T? So T would be M plus L. Understand that? And dt would become dm. So if you differentiate, so L will not come into picture. So in place of dt, dm will come. So in place of dt, bring dm. Understand that? dl was already there. Okay, just keep that as it is, and now you deal with this. Okay, so you can bring this dl here along with an exponential which is the function of L. So that there are two exponentials now. One exponential is in terms of m, another exponential in terms of L. So the exponential which is in terms of L, bring that along with x of L, and the exponential which is the function of m, bring that along with y of m. Just rearranging the terms. You will understand this if you just do properly. Okay, now what is this separately and what is this separately? So in place of L, okay, if you bring T in place of M, if you bring T, what would this look like? This would look like x of k, and this would also look like x of k. Understand? So let's call this as x of k since x of L is there, and since y of m is there, let's call it as y of k. Along with, what is that? There should have been 1 by t here, right? There should have been 1 by t along with this. For this to become what? X of k, there should have been 1 by t. Since 1 by t is not there, I can write this as t into x of k. Similarly, since 1 by t is not there, I can write this as t into y of k. So that is what is shown here. Understand that? So you see this 1 by t I'm talking about. Fine, that is not there here. So associate a t along with this and associate a t along with this before you write that as the coefficients. Fine. So here you have 1 by t. So 1 t goes off. So 1 t remains back. That is why there is a t remaining. So what happened now? What happened now? What is the thing that we have extracted? What is the thing that we have learned? So therefore, we can say convolution in time domain is multiplication in frequency domain along with the term t, which is the fundamental period of x of t and y of t. Understand this? This is convolution property. Now, let's see the Parseval's theorem. Okay, very important. This talks about the power. Okay, now I should tell you. I told you in the introduction chapter, in x of t is a time domain signal where frequency information is not available. How many frequency components are there, and in each component, how many such frequencies are there? Okay, the density in each frequency, how many such frequency components are there? So all that can be available in frequency domain. So this is time domain, this is frequency. In frequency domain, let there be n number of frequencies. All the n number of frequency components are separated. Understand that? So these are the this talks about power at k equal to 0, k equal to 1, k equal to 2, like that. Okay, whereas here all the power is combined. So what we can say through Parseval's theorem is the average power of x of t. The average power of x of t is equal to summation of powers at each frequency. Every frequency component has got some power. Okay, so power at each frequency component can be added to get the average power. So this is the average power of x of t, which is equal to sum of powers at different frequencies. Understand that? This is what Parseval's theorem is. Let's see how it can be proved. See, the LHS is the average power of the periodic signal. This is average power of the periodic signal. We have seen this. We have done this when we discuss energy signals and power signals. Understand that? So you should be aware of this. Okay. So you should be aware of this particular thing. Fine. Now, how to say that this average power equals this powers, the sum of the powers in time domain at different frequencies. Fine. So let's see that. So this is the power equation. The left hand side, what we have is the average power. Okay. The above equation can be written as, now what is this? You know what is this? The x star of t is actually complex conjugate of t. What is complex conjugate? If you have x of t as a plus jb, then conjugate of x of t would be x a minus jb. That j term is there, right? You just have to change the sign of that. Okay, and what would be the magnitude if you just change the, here suppose it is a plus jb, here suppose it is a minus jb. Understand? Both will have the same magnitudes, so that's why it is magnitude square. Understand? So that's why the magnitude square can be written as x of t into complex conjugate of x of t. What I mean is, if x of t is a plus jb, you can just work on. If x of t is x a plus jb, then complex conjugate of x of t would be a minus jb. Whether j is plus or minus, both signals are having the magnitude equal to square root of a square plus b square. This is also square root of a square b square. The magnitude of this also is square root of a square plus b square. That's why it is the same magnitude both are having. So it is magnitude square. Understand that? Now, what happens here? In place of x star of t, now we have written the components of x star of t in time domain. So this is frequency. This is frequency domain. What is the frequency domain component? How can we obtain that? By writing the equation for x star of t. We know what is how to write the equation for x of t. Similarly, they have written the equation for x star of t by having x star of k. Okay, if it is x of t, x of k will come here. If it is x star of t, that is complex conjugate of x, means it's complex conjugate of x of k. So only that is done here. X star of t is being substituted as this. Understand? So changing the order of summation and integration, what can be done? So this summation is brought along with this x of k. Okay, and with the integral, you have this x of t and the exponential. That's it. Okay, so what we have done, the summation is brought with the components, the frequency components, whereas this x of t and exponentials are brought with the integral. Okay, so this is just a rearrangement of the terms that we have in the previous equation. So it looks like this. So what is this? Now, if you see this, if you bring this 1 by t along with this, okay, if you bring this 1 by t along with this, it would be x of k. So it looks like this. And what is that? If you this also has magnitude same, this also has magnitude same. If this is a plus jb, this is a minus jb. Okay, the magnitude of this is square root of a square plus b square. Square root of this is magnitude of a square plus b. That's why we can write this as magnitude square, since both have the same magnitude. Understand? So we can say this is true now. Fine. How did we start? We started with the power. This is the power. We started with the power equation. See, we started with the power equation and operated on that. And we see that we are getting this at the end. So this is Parseval's theorem. Okay. So left hand side is the average power of the signal, and on the right hand side, the sequence x of k whole square. The square of the magnitude is there, right? So it is for x of 0 magnitude of x of 0 square, magnitude of x of 1 square here. They're all distribution of power as a function of frequency. At each frequency, what is the power is what this talks about. So this is called as power density spectrum. Power density spectrum. Understand that? So this is Parseval's theorem, and this can be applied to any signal x of t you have. Okay, the x of k would be the components, frequency components for that in frequency domain. So if for any such x of t, this Parseval's theorem should hold good, is what this theorem tells us. Okay, so we have seen the properties in this particular session. We'll go on with the problems in the next sessions. Okay, so with that we shall end this session. Okay.